error and not area.
Yeah. Yeah, we're looking at the possible propagated error in computing the area of the square. Okay. So what's our thinking on this? Let's go back for a second, and we'll come back to the problem. But let's look at this again, right? This is calculus pictures. A lot of times tell the whole story, right? So think what we're doing here. We've got some function f. In this case, what's our function going to be? It's going to be a, isn't it? We're calculating area based on side length of the square, right? And we know that if we've got some value, call it x, now for us, what's the value going to be? Yeah, it's going to be 10, isn't it, right? So that's the measured value of a side length of the input variable x, right? So we've got some measured value. If that value, that measured value, were to wander a little bit, right? If we were to nudge it to the left or the right, that would cause the value of the function to change also, right? So what we're doing here is we're just saying if there's some error associated with that measurement, call it delta x, plus or minus delta x, then we want to just approximate how much is that little nudge to the left or right from the measured value going to cause the value of the function to change, right? And that's our propagated error, right? And so what this comes down to is then using calculus to make a quick approximation. All we said was we're going to approximate the curve with the tangent line, right? That's why we call this linearization or linear approximation. And as long as we're staying pretty close to home here, as long as we're not going too far away, deviating too far away from x, the curve is well approximated by the line, right? So we could just say, instead of going through the complicated calculation of how much is the value of the function changing, we'll just ask, how much does the y value of the line change, right? And that comes from the fact that if y equals f of x, then we know that dy dx equals f prime of x, right? That's our definition of derivative. And dy is what we're trying to solve for. What's the incremental change in the output value, the y value, going to be for a little nudge of dx to the left or the right? And so we come up with this formula, that we're just going to use over and over. There it is. That's our definition of a differential, right? The change in the output equals the derivative, meaning the slope, times the amount of the nudge to the left or the right. Okay. So let's look at this. All right, so we know that we've got an area function. What is a of x? If x is the side length of the square, what's the area? X squared, sure. And we're just trying to find, dA, aren't we? Right? We're trying to approximate delta A by dA. Use differentials to approximate the possible propagated error. So the amount that the area is going to change, delta A, is approximately equal to the differential dA, right? Okay, so let's add our values here. You already told me x equals what?
X equals
10, good. Plus or minus 1/32. Okay, so then that means that x is 10 and dx is
Plus or minus.
Yeah, plus or minus 1/32. Okay, so what do we do? Sure. Okay, good. So dA dx equals what?
Or the derivative.
2x. Good. So then the differential dA equals,
2x.
2x dx.
well, 2x times
Dx.
dx, right? See, we're just going to take this derivative. Here's our derivative written in normal form, in ratio form, right? dy dx. Think what this means. This means a slope, doesn't it? If we were to graph the area function, this is just going to be the slope of that graph at whatever value of x we choose, right? Okay? If we write it in this form, if we multiply each side by dx, it's no longer a comparison. It's not a slope. Now we're saying how much is the function going to be nudged vertically for a given nudge horizontally on that graph. Okay, so this is the differential form, and then all we got to do is just plug in our values. So we get 2 times 10 inches times plus or minus 1/32 of an inch equals plus or minus what? 20/32. What's that work out to be? 5/8. And what are my units going to be? Square inches, good, or inches squared. Okay. So that's our propagated error. The little measurement error of plus or minus 1/32 of an inch in measuring the side length of our square is going to result in a corresponding propagated error of plus or minus 5/8 of a square inch in calculating the area, right? Okay. Is that good or bad? We don't know yet, right? How would we know? Okay, good. We'll calculate a relative error and just think of it as a percent, right? So it really we can only tell if this is good or bad if we compare dA to the value of A, right? So dA over A equals, and remember, resist the temptation to just plug in values of dA and A, number values. Why don't we say what was the differential dA written as a function, was that, right? So we get 2x dx divided by A, which is just x squared, you told me, right? And so we can actually come up with a relationship here, right? We can divide the top and the bottom by x, and I get 2 dx over x is the function that's going to tell us for any value of x or dx, that's going to tell us what the relative error is, right? So then we could just plug in 2 times plus or minus 1/32 of an inch over 10 inches. Notice the units cancel, right? So we get a unitless number, which is good. And then what are we going to get here? 1/16 divided by 10, so we get 1 plus or minus 160th. Which as a decimal, what's that going to be?
0.625%.
Oh, percent, okay, 0.625%. So now you can tell, I mean, is that good or bad, depending on what are we willing to tolerate?
It's pretty good.
Probably pretty good, you know. Okay. How about, this is kind of a neat trick. This is something, here's a napkin trick. When you're out at a restaurant with your friends, you can impress them in college with your mathematical prowess, and you can do something like, you could make a pretty good estimation, a pretty darn good estimation of what's the square root of 102. Okay, how do you think you could do that? Suggestions. How in the world could we use what we're doing right now to come up with a reasonable? What function are you evaluating when you plug, with the square root of 102? Square root function. Thanks. Square root function. Okay, so what if we take the function f of x equals the square root of x, okay, and we could even graph that if we wanted. We know what that looks like, right? Something like that. And we're going to go out here to 102, and we want to make an estimate of what the y value is there. Okay. Can you think of a way that you could use a differential?
Use it. Have your error be 2.
Okay, yeah, Evan, what were you going to say? Say it again.
Do square root of 100 with an error is
plus 2.
There you go. Okay, well, because we know that 100 is a perfect square, right? So we know what the output is of the function for the square root of 100. If we just did, 2 is pretty close to 100, right? I mean, 102 is pretty close. 2 is not close to 100. 102 is pretty close to 100, right? And so that's a relatively small nudge to the side. And so we could use a linear approximation then to just make a quick and easy approximation of what would this function approximately give us if we nudge it to the side by 2. It's going to nudge it up a little bit, right? Okay, so there's an idea. It's difficult for us to think in terms of radicals because there isn't a good algorithm for calculating radicals, right? It's difficult. But if we use a linear approximation, this isn't curvy anymore. Now we're just talking about a line. Well, lines are pretty easy, right? So let's do this. Let's say that f of x equals the square root of x. We're going to choose x to be 100 and dx is going to be 2. Okay. So if f of x equals the square root of x, what's f prime of x?
1 x to the negative 1 half.
Okay, good. So 1/2 x to the minus 1/2, which is the same thing as saying 1 over 2 times the square root of x, right? Okay. So then let's use our let's use our approximation, right? So y is going to equal approximately. It's going to equal f of x plus. It's going to equal exactly f of x plus delta y, isn't it? Our new y value. Does that make sense? The value of square root of 102 is going to be the square root of 100. X is 100, right? Plus the amount that our function is going to change. But we can approximate that by dy. Okay, so what is dy then? If f prime, well, dy dx equals f prime of x. So what's our differential formula again? dy equals? Good. Okay. So we could say y is approximately equal to f of x plus dy, right? And that's going to give us f of x plus f prime of x dx, and we can just plug in the numbers, right? So we're going to get the square root of 100 plus, well, I'm going to do one more line. Because we went through the hassle of calculating f prime, didn't we? So we got f of x plus 1 over 2 times the square root of x times dx. We'll just put that up top, right? And so we end up with the square root of 100 plus dx was 2 over 2 times the square root of 100. So what's that give us? We can do that stuff in our head. 10 plus
110.
Try it. Guarantee that's gonna be pretty good.
The actual square root is like 100.0995.
Yeah. Okay,
Almost
so
102.05.
not bad, right?
It's really close. You'd need a big napkin.
I don't even think you need to write anything down.
Mhm.
If you do this a couple times, you can do it in your head. Seriously, try it. Tell me what the square root of, no, tell me what the, okay, we'll do square root. I want to know what's the square root of 24. First time, just write it, just scratch something down. Napkin size though, can't make it too big. It's got to be napkin size. But then this is a pretty good little algorithm for just estimating a square root. And you're always going to get, would you agree that you're always going to get the same thing? This is going to be the same every time, isn't it? Right? I mean, the square, or the f prime of x isn't going to change if f of x is the square root of x. You just got to think in terms of what's your x and what's your dx going to be, right? So the square root of 24.
4.9.
4.9. Okay? Let's think how we get that. So the only difference here, everything's the same. The only difference is going to be what's our x and what's our dx, right? So what's x in this case? Good. What's dx?
-1.
-1, right? Okay. So we're going to get 5 plus -1 over
2 times square root of 25.
2 times the square root of 100, or 5, or 25, sorry.
Which is
So, right, 2 times 5. So we're going to get 5 plus -1/10, so it's 4.9. Yeah. Now, what do you think? Now, without plugging numbers into your calculator, based on the shape of a square root graph, do you think that this is going to be more or less accurate than this one?
less accurate.
Exactly.
It's going to be, well, it's actually probably going to be fairly close to exactly the same. But it's, which one would you anticipate? I guess it's really, it's kind of we can have a debate on this. Somebody, let's do that. Let's break the room up. We don't care what the answer is. I just want a good debate. So here's the dividing line. I want to know, Nick, why do you think you're a good debater? I want to know, why is it that you think that this one is going to be more accurate? I don't care if you're right or wrong. Why are we going to get a better approximation? Or maybe you just came in when we were doing this though. Maybe that's not fair.
Is there one previously?
Yeah.
Can I see it right
Yeah,
now?
here's the one we did previously. We said we were going to approximate the square root of 102.
Yeah.
Okay. So what's the argument for why the square root of 24 should be more accurate?
Because it's a smaller value. So the square root is going to be more nearer to the...
Okay, so by smaller value,
Well, I'd say, like, for the 102, we changed our error by 2.
okay, so the
Where's the
nudge
error?
was 2, and this
And
time the
the
nudge
nudge
was 1, right?
So-
So good, so there's the argument for why it should be more accurate, because we're closer to the point of tangency. What's the argument for why this one should be more accurate?
I don't have a right.
Okay,
Because it's relatively closer, because the total quantity of numbers involved, even though it's 2, the other difference is 1,
okay.
because of the total quantity.
Ah,
it's
okay,
closer.
that's a good one. Okay, that's a good one, right? Because 2 100ths is less than 1 25th. You got another idea? There's another way we could say, just based on the shape of the curve.
It just gets flatter and
Ah,
farther
okay,
you
yeah,
get
it's the
above.
function is flatter here, it's curvier here, right? The further you go along the square root function, the more linear it gets. Does that make sense? Okay, the curvature flattens out, and so approximations will be better. It's more like a line. Does that make sense? That kind of thing, if you take the extra 30 seconds sometimes when you're doing a problem and think about it in terms of that stuff, because that's how you really get to get good at math. If you start thinking about not just the X's and O's, right? If you think about conceptually, what are the big broad scale relationships going on here, right? Okay, what about, okay, let's try one. So you got a good algorithm for impressing your college friends on your prowess at estimating square roots. Let's do a, how about if we do a power this time? Let's do something like, what is 1,000 and, what's 1,000.1? 100.1 squared. 100.1 squared. Okay. So whoops. We're going to approximate that. Okay, what's our function? What function are we evaluating when we might ask that.
X squared.
X squared, yeah. Okay, so we're evaluating f of x equals x squared. So then what's our differential gonna be for that?
2
2x
dx.
dx, right? Okay, what's our x?
Or 100.
100, okay. What's dx? Okay, right? And so we got this then, right? So our answer, so y is gonna be approximately equal to f of x plus dy, right? Plus f prime of x dx, right? We can do this, that's no big deal. What is 100 squared?
10,000.
10,000, right? 1 and 4 zeros, okay? So this is, let's put our numbers in. So we get x squared plus 2x dx, right? And so we're going to get 100 squared plus 2 times 100 times 0.1. Okay, we can do that. That's a 1 and 4 zeros plus 200 times, well, what's 100 times 0.1? 10 times 2 is 20.
10,000.
10,020. See how we did?
It's 10,020, like 0.01.
Yeah. Pretty amazing, huh? That's, if you practice that for half an hour, you could be good at these algorithms. So, yeah, that's not bad. We were within 100th of the correct
I
answer.
think it'd be more impressive if it's cubic.
Well, cubic's no, it would be, and cubic's no harder.
Like,
Okay, I'm sold. Let's do a cubic one. All right, what is, I want to know
It's like
what
the same thing,
is,
but it's more impressive if you do it.
okay, so what's 9.02 cubed? So what's our function? So what's our differential?
3x squared.
Okay, good, so 3x squared dx, right? Same every time. We know that y is approximately equal to f of x plus f prime of x dx, right? So it's just, in this case, we're just gonna get x cubed plus 3x squared dx, plug in the numbers, no big deal, right? So what's that give us? 9, x is 9, dx is 0.02, right? So we're gonna get 9 cubed plus 3 times 9 squared times 0.2. Okay? Did I do that right?
0.02, isn't it?
Oh, 0.02, yep, you're right. That even makes it more impressive.
Yeah.
So what's that give us? 9 cubed is, too slow, 729, plus 3 times 81, what's that?
243.
243 times 0.02. Well, what's 243 times 0.01? 2.43 doubled,
4.86.
4.86, right? So what do we get? 733.86. See how we did? That's pretty close. Once again, we're about 100th off. That's not bad, right? We'll take that. Okay? All right, I think that's another important one to do here. We got, oh, I know, yeah. I know what we gotta do. Gotta find one like so. Maybe I'll make one up. Okay, they don't have one, but I'm gonna make you do one. This is pretty cool. Okay, we could do something like this then. Let's say, okay, let's say that for a, we'll do something easy. Start off with here, we'll do a circle. Okay, so I'm telling you that we have a circle of radius 12, and we need to be able to calculate area to within plus or minus 0.01%. Okay. What's the max allowable measurement error? For R. Okay. So what are we looking for here? DR, right? DR. Okay, so we want to know what's DR. How can we set this up? What's our function? Area. Okay, good. So we got area as a function of radius is pi r squared. So what's our differential? dA equals 2 pi r dr, right? Okay, and then what does this mean? If the maximum, we need to be able to calculate area to within plus or minus 0.01%.
Well, that's DA over.
Okay, so dA over A has to equal plus or minus, the maximum would be plus or minus 0.01%. So how do I write that? 0.0001. There you go, right? Okay. Well, what is dA over A? Well, that's just going to be 2 pi r dr over pi r squared, right? I can whittle this down a little bit, right? Good. Cancel the pi's, cancel NR.
Wait, is that enough zeros?
Say it again.
Oh, never mind, never mind.
So 2dr over r equals plus or minus 0.0001. All I got to do is just solve for dr, right?
And R equals 12.
Yeah, so dr equals plus or minus 0.0001 r over 2, which is equal to plus or minus 12 times this would just be 0.0012, good, divided by 2.
0.0006.
And whatever we're measuring it in inches or meters or whatever. So that's our maximum allowable measurement error if we want to keep the area within our tolerances, right? You can work backwards on this too. If you know what the outcome needs to be, you can work backwards and say, okay, then what does our measurement accuracy need to be, right? Our precision. Okay? Make sense? Okay? All right. We can call that a day. Pretty good.